Trigonometric substitution is another technique of integration that we can use to integrate integrands that are of the form of a squared plus u squared, a squared minus u squared, or u squared minus a squared. Now a lot of times these are underneath a square root sign or to some power, but basically they're the sum or a difference of perfect squares, and if they're not a perfect square yet, we can make them a perfect square by completing the square. Now if we have something of the form a squared plus u squared, just like the name says, substitution, I'm going to create a substitution. The substitution that I'm going to use here is going to be equal to letting u equal a tangent theta. Now if we have something that's a squared minus u squared, of course a is a constant, u is some variable component. So if we have something that looks like a squared minus u squared, we will let u equal a sine theta. And you'll definitely either want to have these memorized or have them on your note card for the exam. Now if we have something u squared minus a squared, that's going to be a secant, so u would equal a secant theta. So these are the substitutions that are going to be used in Trig Sub. Now some of these already look familiar. This looks like it's close to the form 1 over a squared plus u squared that we learned in trig integrals, and the same with sine and secant. So there is a connection there. Now along with these, we also need to remember our Pythagorean identities. Now the Pythagorean identities we've talked about quite a bit, but let's go ahead and write them down one more time. Sine squared plus cosine squared is 1. And of course we can solve this for sine squared or cosine squared if we want. We also have 1 plus tangent squared is equal to secant squared. And it seems like this one shows up an awful lot. And our last one that we could look at is 1 plus cotangent squared of theta equals cosecant squared of theta. Now if you just look at our substitutions right up here, you can see that cosecant and cotangent don't show up with any of these, but that's okay. Sometimes we're going to use this Pythagorean identity when we're integrating after we use the u sub, so it's important to remember those as well. Okay, so once we get a problem with the u sub and I make my substitution, there's a particular process that we need to make sure that we follow. Now my first introduction to this is going to be looking at a problem that doesn't necessarily require Trig Sub, but is familiar to you. So let's go ahead and look at the problem, the integral of 1 over 4 plus x squared dx. Now notice I don't have a square root sign here. Usually Trig Sub involves a square root sign or a power of some sort, but it doesn't have to. Now from previous sections, this fits a trig integral. And it fits the form integral of 1 over a squared plus u squared du. And that would integrate into 1 over a inverse tangent of u over a plus c. So that was from a previous section. This is one of the identities, or one of the inverse trig function integrals that we have memorized. So if we were just to work this problem real quick, this would be 1 over 2. The reason it's a 2 is, remember, this has to be written as 2 squared plus x squared, inverse tangent of u, which is x over 2 plus c. So this is my answer right here. So you can see really fast, if you recognize the form, some of these can be pretty short. So don't always go after Trig Sub. Sometimes it's a little simpler than that. So we're going to do the same problem, but with Trig Sub now. Now when we're using Trig Sub, we always want to rewrite this as 2 squared plus x squared dx. So this is of the form a squared plus u squared. And remember from the beginning, the rule was if we had something like an a squared plus u squared form, and this could be in the numerator or denominator, doesn't matter which, it's said to let u equal a tan theta. So in this particular case, u is equal to x, a is equal to 2, so x is equal to 2 tan theta. So if I start using my sub, just like Trig Sub implies, here I'd have a 2 squared, and then I'd have an x. X is equal to 2 tan theta, and of course that's squared as well. So 2 squared plus 2 tan theta, quantity squared. Now if I take my derivative here, dx is equal to 2. The derivative of tangent is secant squared of theta d theta. So I have to make sure I remember to make that substitution. Now this is a really common thing to forget, to take that derivative and substitute it in, but there it is. Now what we have to do is simplify the heck out of this thing. So in the numerator there's really not much I can do. I have my 2 secant squared theta d theta. Now in the denominator I have 4 plus 4 tangent squared theta d theta. And then like I said, we have to simplify. Denominator, I'd factor out a 4. And then I recognize a trig identity here. I guess I could cancel the 2 into the 4 and pull that half out front. So the numerator is secant squared theta d theta. Now the denominator, 1 plus tangent squared, we know from our trig identity is secant squared. So 1 plus tangent squared is secant squared. The secant squareds cancel, and this is kind of an interesting integral. It's basically 1/2 d theta. 1/2 the integral of d theta. Well, the integral of d theta is theta. But my original was in terms of x, if you'll recall, and so should my solution be. So what we need to do is we need to use a triangle here to help us kind of back solve into x's. So from here, if you'll recall, from above, I let x equal 2 tan theta. Well, if I solve for tan theta here, I get tan theta equal x over 2. Now if you remember your right triangle trig, the acronym SOHCAHTOA, better put it in order, SOHCAHTOA. This gives the ratio of our trig function. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. So in this particular case, I'm looking at tangent is opposite over adjacent. So if I draw a quick right triangle, and when you put these on your homeworks and exams, make sure you always mark your angle that you're using, theta. And then tangent is opposite over adjacent. Now using Pythagorean's theorem, I know that x squared plus 2 squared is equal to the hypotenuse squared. So the hypotenuse would be equal to x squared plus 4. Now notice there's a relationship here. Square root of x squared plus 4. And then over here we have this x squared plus 4 as well. So there's a connection there. It's not guaranteed it's going to be the square root up here, but there's a connection. The x squared plus 4 shows up again. Okay, so now what I know, and I didn't have to use this triangle for this problem. I could have just gone after this bit right here after the tangent theta equals x over 2, but it helps to see this triangle because you're going to need to use it in other problems. I need to know what theta is, so I'm going to work with this bit right here. Theta is the inverse tangent of x over 2. Okay, so that comes from right here, and then substituting back in, I end up with 1/2, and then theta is equal to the inverse tangent of x over 2 plus my constant of integration. Now, quite a while back, we ended up with the same problem up here, the same solution up here, I should say. And the reason we ended up with the same solution is that we have the exact same integrand, just a different method. So 1/2 inverse tangent of x over 2, I end up with the same either way. So when you're working through these, make sure you remember there could be other methods. There could be an easier method, or there could be a harder method. So it's good to keep your eyes open for our basic trig integration techniques that we've learned earlier, because you won't always have to go after one of these trig sub, although I do really like the trig sub. Now one of the main reasons for using trig sub is when we have something that's familiar to us of a particular form, but because a radical is involved, I can't actually finish the integral. So let's go ahead and look at an example where we have a radical involved. Well, let's say we have 324 minus x squared dx. Now this one's difficult to look at right now and see that it's a difference of perfect squares. 324, the square root of 324 is 18, so I can rewrite this as 18 squared minus x squared dx. Now as soon as I see that, this is of the form a squared minus u squared, 18 squared minus x squared, And so this means I should let u equal a, no, it wasn't tan, was it? A squared minus u squared was going to be equal to u equal a sine theta. So du, a is equal to 18 sine theta. Now this is the most common thing to make a mistake here, is to forget to use your substitution. So u was equal to x. So we need to make sure we include u is equal to x. And then I take the derivative. This is the common forget. The derivative of sine is cosine of theta d theta. So don't forget that piece. Now just like it says, we substitute in trig sub. So in place of this dx, I need to have 18 cosine theta d theta. Now in the denominator, I go ahead and sub in as well, and I just have my 18 squared minus x squared. Now x was 18 sine theta, and this is quantity squared. So here's my substitution, and now I need to simplify this. So denominator, I'll start with that. This is 18 minus 18 sine squared theta, and of course this is square root. And my numerator is 18 cosine of theta d theta. Now in the denominator, there's a bit of a trick here. I can factor out an 18 under that radical, and I'm going to be left with 1 minus sine squared theta. And then my numerator is 18 cosine of theta. Okay, continuing to simplify. Notice when we're working here, I have a mistake. This was 18 squared. So this is 18 squared. This is 18 quantity squared, so this is squared as well. So this is squared too. Okay, so I can split up the radical, 18 squared. I can split up a radical across a product. Square root 1 minus sine squared theta. In my numerator I have 18 cosine of theta d theta. Okay, continuing to simplify. You'll notice that the square root of 18 squared is just 18. 18 divided by 18 is 1. Now that's not always going to happen, so always double check that. Now the square root of 1 minus sine squared. 1 minus sine squared is cosine squared, and remember I still have my radical here. Square root of cosine squared is cosine. And once again, we have everything canceling, which does not leave us with a 0, but it leaves us with a 1. So this is the integral of d theta. Now if we look at this in terms of the integral of d theta, this is just going to be equal to theta plus some constant of integration. But we need to convert back. And my original variable was x. So the way we're going to convert back to x is to use that original substitution to help us make that triangle key. So our original substitution was x equal 18 sine theta. So if I solve for sine theta here, I get sine theta equals x over 18. And then to solve for theta, I would take the inverse sine of both sides, so this would be the inverse sine of x over 18. Okay, so again, inverse sine of x over 18. So this would equal inverse sine of x over 18 plus c, which is your constant of integration. Now this is kind of interesting. I could have also put up my triangle. I didn't need it here, but I could have. And this would have been opposite over hypotenuse, so opposite over hypotenuse. And this side, this missing side, would have been 324 minus x squared. Now, if you look at our original problem, there it is, 324 minus x squared again. And I could have solved for not only just inverse sine, I could have used inverse cosine, adjacent over hypotenuse, inverse tangent, opposite over adjacent. So I didn't have to use inverse sine to solve this. It was just easier because that was my original substitution. So keep that in mind when you're looking at some of these, especially if you're checking your answers on like Wolfram Alpha or Mathway. They could have solved for a different inverse trig function at the end to complete the problem. It's equivalent solution. You just have to realize where that came from. It came from this triangle key where I can use this to solve for my other trig functions as well. Now, like I said, usually a square root sign is involved, but it doesn't necessarily have to be, and sometimes a square root sign is involved and some extra information is involved as well. So let's go ahead and look at an example where we're looking at, let's say x squared in the denominator, square root of 361 minus x squared dx. Now, as we're looking at this, we have to start trying to rewrite this into a form of an a squared or u squared plus or minus a squared. So difference of perfect squares basically. The square root of 361 is 19. So this looks like 19 squared minus x squared dx. So as soon as I see this, I can make the substitution. This is of the form a squared minus u squared. A is 19, u is equal to x. So the substitution here is to let u equal a, and again this is a squared minus u squared, so we need to remember what that substitution is from our list up above, and that substitution is to let u equal a sine of theta. So u is equal to x, a is equal to 19 sine of theta. So dx is equal to 19, the derivative of sine is cosine of theta d theta. So again, this is the thing that people forget the most, so make sure you always find that dx and make that substitution. If you don't, usually things won't cancel and simplify, and it makes things really difficult. Okay, so we have a lot to substitute here for. So the dx we know is equal to 19 cosine of theta d theta. Now x squared, it's not under the radical, it's 19 sine theta quantity squared. And I have my 19 squared minus x squared again. So this is 19 sine of theta quantity squared. So everything's subbed in. I'm going to put my d theta at the end here. So again, I have to not just write x, but I have to have it squared, and so I'm squaring the 19 and the sine. There's a lot of simplification here. It looks like in the numerator there's not too much to do. In the denominator I have 19 squared sine squared theta, and then under the radical I have 19 squared minus 19 squared sine squared theta. And again, numerator not very exciting at this point, but hopefully we'll get something to cancel. Okay, rewriting again. It looks like I can start canceling a little bit here. I have this 19 will cancel with one of these 19s in the denominator. So I'll have 1 over 19 integral sine squared in the denominator. Probably should have started a new line. I can factor out a 19 squared under the radical, and I'm going to be left with 1 minus sine squared of theta. In the numerator I just have a cosine of theta now. If you'll recall, what ended up happening here was this 19 canceled with one of these 19s. Okay. Again, simplifying, I have this 1/19 out front. Cosine theta is in the numerator, but I'm going to work on the denominator first. I can split up this radical into root 19 squared, root 1 minus sine squared of theta. And in my numerator I have that cosine of theta d theta. Okay, these are not short problems, and there's lots of steps to show, so don't skip any of them. Now I see this square root of 19 squared is 19, so I can pull out another 19, and I'm going to write these separate just so we see that another one was pulled out, so that came from here. Sine squared theta. Now 1 minus sine squared is cosine squared, so under the radical I have cosine squared theta. In the numerator I have a cosine of theta, and of course my d theta. Don't drop your differential. So now I have 1 over 19 squared integral. Now the square root of cosine squared is cosine, so the cosines cancel. 1 over sine squared is cosecant squared. So I can rewrite this as the integral 1 over 19 squared cosecant squared of theta d theta. So that gets us to a point where we can actually integrate. And if you want to look at this, remember 19 squared we found up here was 361. That's what we originally started with. So I have 1 over 361. Now the derivative of cotangent is negative cosecant squared, so the integral of cosecant squared is a negative cotangent of theta. And of course we have our constant of integration, which we really don't need quite yet because we still need to convert this. We need to convert back to x. So the way we're going to convert back to x is we go back to our original substitution that we made. So our original substitution is right here. It was x equal 19 sine theta. So let's recall x equal 19 sine of theta. That tells me that the sine of theta is equal to x over 19. Remember the SOHCAHTOA, sine is opposite over hypotenuse. And I guess I could write that out a little bit so it doesn't look like a 0. So opposite over hypotenuse. So let's go ahead and draw out that triangle. Now when you draw out this triangle, you have to show that it's a right triangle, because if it's not a right triangle, SOHCAHTOA doesn't apply. And you always need to mark your angle that you're using. So opposite over hypotenuse. Now the adjacent leg then, using Pythagorean's theorem, would be 19 squared, which is 361, minus x squared. Now this radical, root 361 minus x squared, let's look up here. See how it appears up here as well? It's almost like a little checkpoint that you can depend on for that sum or difference of perfect squares to show up again in the problem. Now from here, what I'm going to do, I have negative 1 over 361 cotangent. Now cotangent, remember tangent of theta would be opposite over adjacent. So cotangent would then be adjacent over the opposite leg. So this would be my solution. Of course, I'll clean it up just a little bit. And as we're cleaning this up, let's remember our constant of integration as well. So this is equal to a negative square root 361 minus x squared all over 361x plus your constant of integration is plus c. Now sometimes these are simplified quite a bit, so you'll have to, if you use the help me solve this, review an example. Sometimes they do a different substitution to a different trig integral in between, but this one is pretty straightforward. We really can't do that. So tangent was opposite over adjacent, so cotangent was my adjacent leg over my opposite leg. And remember, I get this root 361 minus x squared using Pythagorean's theorem. Leg squared plus leg squared equals hypotenuse squared, and then I solve for that missing leg. So this one was pretty interesting because, clear up here at the beginning, I had this extra x squared involved, and so I had to deal with that in my substitution. And so you have to be really careful that you don't drop that or forget about it, because if you do, the problem is going to be a really different solution. Okay, so you have to consider all of those parts. Now this next one, we're going to have a radical involved as well, but instead of just being the square root, it's going to be the cube, the third power of the square root. So let's go ahead and look at 1 over the square root, actually let's do to the 3/2, x squared minus 484 to the 3/2. So there's a square root involved here because 2 is the root, 3 is the power, dx. So let's go ahead and rewrite this first. Let's recognize that 484 is a perfect square. That's going to be 22 squared. and then all of this is raised to the 3/2. Now there's an error that I've been seeing a lot on handwritten homework and on exams, so let's go ahead and talk about that real quick. A lot of people are looking at something, let's say like x squared plus 16 to the 1/2, and they're saying, oh, that's equal to x squared to the 1/2 plus 16 to the 1/2, which would simplify to x plus 4. That's not true. I can't do that here. The exponent, or the radical, because remember I could rewrite this as the square root of x squared plus 16, does not equal x plus 4. It does not simplify like that. So this is a mistake. Now let's figure out why that is by plugging some numbers in. So if we had the square root of 9 plus 16, that's the square root of 25, which we know is 5. So this is right. Now the wrong way to look at this is to take the square root of 9 plus 16 and say, oh, that's root 9 plus root 16. The square root of 9 is 3, square root of 16 is 4, and this is equal to 7. This is wrong. If I got my 5 back out of this, there are some cases I guess that could happen, but for the most part it's showing me that this is the wrong process to separate the radical. So I cannot rewrite this. I cannot split these up. So keep that in mind while you're working, because like I said, it's a common mistake that's showing up quite a bit. Okay, so let's go ahead and rewrite our original problem. So this is the square root of 1 over x squared minus 22 squared to the 3/2 dx. Okay, so let's go ahead and see if we can recognize the form that this comes in. So x squared minus 22 squared. This looks like a u squared minus a squared. And the substitution that we should use for u squared minus a squared is to let u equal a secant theta. U in this case is x, a is 22. And again, the common mistake here is to forget to take our derivative. The derivative of secant theta is secant theta tangent theta. And again, always put parentheses around the arguments of your trig functions. Okay, so now we sub in. And again, the most common mistake to make is to forget that sub in for dx. Now x squared. X is 22 secant theta, so x squared would be 22 squared secant squared theta minus 22 squared. So all of this is raised to the 3/2. Now in my numerator, I just have my dx, which is equal to 22 secant theta tangent theta d theta. Okay, rewriting. Now notice I have this 22 I could pull out front. I could leave it in as well, but I'm just going to pull it out front for now. In my denominator, I also have a 22 squared that's common. So I have this 22 squared that I could factor out, and it'd be left with secant squared of theta minus 1. Now all of this is raised to the 3/2. Not just the secant squared theta minus 1, but the 22 squared as well, so that's why it's all in brackets. And then my numerator is secant theta tangent theta. And of course my d theta, don't forget that. Okay, simplifying. I have my 22 out front. Now this denominator, I have this 22 squared, and it's raised to the 3/2 power. And then I have the secant squared minus 1, which should feel kind of familiar. That's one of our Pythagorean identities rewritten. That's equal to tangent squared of theta, and that's to the 3/2 power. And in my numerator, I have secant theta, tangent theta, d theta. Okay, so rewriting. This 22 squared to the 3/2, when you raise a power to a power, you multiply the powers. So this is, the 2's would cancel, and I'd have 22 cubed out front. So I have 22 over this 22 cubed. And then I have my integral. I have secant theta tangent theta in my numerator. And then in the denominator, I have tangent squared to the 3/2. And again, when you raise a power to a power, you multiply the power. 3/2 times 2, the 2's would cancel, and I'd be left with tangent cubed of theta. Okay, so I can see the coefficient out front. I can simplify just a bit. So 22 over 22 cubed would be 1 over 22 squared. And then it looks like I need to start doing some rewriting here. And when we're doing these rewrites, we need to start thinking about antiderivatives and trig derivatives and integrals to get this into a form where I can integrate it. So I have this canceling occurring. So I have secant theta over, in the denominator it looks like I have tangent squared of theta. Now the derivative of tangent is secant squared, so I don't have a nice little u du here. 22 squared was 484. So one of my other ways that I could work with these is I could rewrite these in terms of sines and cosines, and then hopefully something would pop out of this. Now when I divide by a fraction, tangent is sine over cosine, I multiply by the reciprocal. So this cosine pops up top. So again, when you divide by a fraction, you multiply by that reciprocal. This cosine cancels with one of these. This actually isn't looking all that much better, but looks better soon. And then it looks like I have cosine of theta over sine squared of theta. Okay, well sines and cosine are u du's of each other. So I think that we could use a really old integration technique, just good old u substitution here. So we could let u equal sine of theta, and then du, the derivative of sine, would be cosine of theta d theta. And we've got that. That's good. So I have the 1 over 484 out front. Integral. Cosine of theta d theta is equal to du. So cosine theta d theta is du. And then sine is u, so this is 1 over u squared du. And of course I'd flip that up top to integrate it. So this would be u to the negative 2 du. Now, it's been a while since we've integrated something this straightforward. But remember, you add 1, divide by the sum. So if I add 1, u to the negative 2 plus 1 is u to the negative 1 divided by negative 1. So I have a negative 1 over 484 out front. And then I have sine, u is sine, to the negative 1. So I have 1 over sine of theta here. And of course I could have my plus c, except I need to convert this back. Okay, so to convert back, I come clear back up here to my original substitution that I had. And my original substitution was to let x equal 22 secant theta. So if I solve for secant theta here, I get x over 22. Now secant is 1 over cosine. Cosine is adjacent over hypotenuse, so this is hypotenuse over adjacent. So hypotenuse over my adjacent leg. And this missing side then would be equal to, and again we can come up here and have a look, it should have something to do with x squared minus 484. And indeed, it is x squared minus 484 if I use Pythagorean's theorem to solve. So I come back up here and I have negative 1 over 484 times 1 over sine. Well, sine is opposite over hypotenuse. So my opposite leg to here would be that root x squared minus 484 over the hypotenuse, which is x. But we won't leave it like this. When you divide by a fraction, you multiply by the reciprocal. So this flips up top is to x, square root of x squared minus 484. It's kind of squeezed in there, so let's go ahead and write this out. So we could write this as negative x over 484 square root of x squared minus 484. and then a plus c, your constant of integration. Now remember, all of these so far that we've been working with are indefinite integrals, but you could evaluate these on, remember, evaluation, always do upper minus lower. When we're not doing any definite integrals with these in the problem set that we're looking at right now during the lecture, because it just adds so much length to it, and that's something that we're already familiar with doing, and I'd rather focus on the new integration technique. Now some of these can get pretty dicey. These get very, very long. And what you need to remember is you just can't give up. You just have to keep working at them. Now there's an integral that we worked at up here. I think we looked at a secant. Let's see. No. Okay, so in our previous lectures with integration by parts, we integrated secant cubed. It was the recursive method. And sometimes we also run across just integrating secant. And so there's a couple of hints that I want to give you for that. So those hints will come up in the middle of this problem. Let's look at the integral of, let's do a complete the square. Oh, we have some pretty good options here. Let's go ahead and look at the integral of x squared plus 2x plus 26 under the radical, and let's square root that. Okay, these are long problems, so I was trying to look through my problems to make sure I didn't duplicate anything, because these do get to be a little bit long. Now notice this is not the sum or a difference of perfect squares, so I need to complete the square on this. And hopefully when I complete the square, I get it into an a squared plus u squared minus a squared minus u squared form. So let's look at completing the square. And again, this is an old algebraic technique. So completing the square, I take half my linear term. So I take half of this value and I get a plus 1, and then I square it. So 1 squared is 1, so I add 1. Now, if I'm completing the square in an expression, not in an equation, if I add 1, I also have to subtract 1. Now, if we look at x squared plus 2x plus 1, that factors into x plus 1 quantity squared. So if you want to look at that, it's x plus 1 times x plus 1. 26 minus 1 is 25. So this is x plus 1 quantity squared plus 25. So now this is the sum of perfect squares. So this is ready to go. So as soon as I get it into this form, nothing has really changed here. Same process I always go through. However, instead of just having x is equal to, or u is equal to x, I have u is equal to x plus 1. So this is of the form u squared plus a squared. So my substitution here is to let u equal a tan theta. So in this case, u is equal to x plus 1 is equal to a. A is the square root of 25, which is 5, so I guess I could write this as 5 squared tan theta. Solving for x, I get a negative 1 plus 5 tan theta. Taking my derivative, the derivative of a constant is 0. The derivative of tangent is secant squared d theta. So process isn't that much different. We just need to remember that we have a binomial now instead of a monomial for my x. Now again, the most important thing to do here is to forget our dx, so let's not forget that. Now x plus 1. X plus 1 is equal to 5 tan theta. So I'm taking that and squaring it. And then in my numerator I have my dx, which is equal to 5 secant squared of theta d theta. And then I just simplify the heck out of this. Lots of algebra here. So in the denominator, 5 tangent theta, I can square, can distribute the exponent across multiplication, but not addition or subtraction. So this is going to be the square root of 25 tangent squared of theta plus 25. And you can probably already see where this is heading. I can factor a 25 out of that denominator, still under the radical. So factor out that 25. I'm left with tangent squared of theta plus 1. Now under this radical, I can take the root 25, root tangent squared plus 1, because I can separate the radical over a product, just not a sum or a difference. So I'm left with tangent squared of theta plus 1. Square root of 25 is going to be equal to 5, so these cancel. Now tangent squared plus 1 is equal to secant squared, so this is the square root of secant squared of theta. And of course the square root of secant squared is secant. So this is the secant of theta. My numerator is secant squared of theta. And canceling occurs here, and I'm just left with the secant theta in my numerator. So this is one of those integrals that I wanted to talk about specifically. So this is the integral of secant theta d theta. There's no antiderivative here. There's no straightforward solution to integrating this, but there's a trick to it. And this is the trick. You multiply very specifically by secant theta plus tangent theta. So this is the trick to integrating secant theta. Now, a lot of textbooks have tables of integration, and you would just look this up and you'd pop down the answer. But we want to know how to integrate this by hand. So if you ever come across this on a homework or a test, you need to make sure that you're showing your work and doing it by hand to get your credit. So this secant theta is going to distribute, and I have secant squared of theta plus secant theta tangent theta all over secant theta plus tangent theta. Now this actually looks worse, but we'll see here with a nice little u substitution it pops right out. So u is equal to secant theta plus tangent theta. The derivative of secant is secant theta tangent theta. And the derivative of tangent is secant squared of theta d theta. And if you notice, that's du. I have all of that up here in my du. So this is just 1 over u du, which is natural log absolute value of u, but u was secant theta plus tangent theta. Now we've done so much work here, it would seem like we would be done. I mean, this problem started way up here, but we need to convert back to x. So to convert back to x, we come back up here and we use our substitution. We have x plus 1 is equal to 5 tan theta. So if I solve for tangent of theta, I get x plus 1 over 5. Now remember, that's opposite. Tangent is opposite over adjacent. So I have my right triangle, and it has to be marked as a right triangle, and it has to look like a right triangle. I always mark my angle theta, and again that's opposite over adjacent. Okay, so if I use Pythagorean's theorem, I end up with x plus 1 quantity squared plus 5 squared square rooted for the hypotenuse. Now if I simplify that, that would be x squared plus 2x plus 26. And you can see kind of our checkpoint right back at the beginning. Here's my x squared plus 2x plus 26. So I need to convert this back. So this is equal to the natural log absolute value secant. Now secant is cosine, 1 over cosine. Cosine is adjacent over hypotenuse. So this should be the hypotenuse over the adjacent. Now tangent, I already have. It's opposite over adjacent, x plus 1 over 5 plus c. That's my constant of integration. So this would be my solution. Now, there's a couple things I want you to be aware of. I could rewrite this several different ways. x plus 1 quantity squared in my math lab and on your handwritten homework, so we're going to ask you to simplify. So if I expand this, x plus 1 quantity squared is x squared plus 2x plus 1. 1 plus 5 squared is 26. So this is x squared plus 2x plus 26 is what I started with, plus x plus 1 all over 5. So this would be the simplified solution. Now I'm going to take this one step further. Now remember, the log of a quotient is the difference of the logs. So sometimes you'll see the answer written like this. Minus natural log absolute value of 5 plus c. Now natural log of 5 is just a constant. So what ends up happening here is this combines to like a super constant. And they just combine into 1 plus c, one value of a plus c. And so a lot of times when you're working through these, or when you check your answer on Wolfram Alpha, or help me solve this, you won't even see this denominator because it gets soaked up in this constant of integration because it's just another constant. So this would be another way you might see that solution. I am fine as combining these with a common denominator. Really important here, I need to simplify what's under this radical into x squared plus 2x plus 26. So these are really long problems. I would like to do one more. Let me check to see how long it would take. It took me, when I worked through it, looks like it took me 2 pages. Maybe it's not worth looking through, but I want to get you started with a quick reminder here. So, reminder. If you run across any problems where you're trying to integrate secant cubed of x dx, we have looked at this, I believe, back in integration by parts. So I just want to give you a quick heads up on this. What we would do is we would rewrite this as the secant of x times the secant squared of x dx. And remember, you choose a u and a dv. So that would be secant squared of x for my dv because I can integrate it, and secant of x dx. du then, the derivative of secant, is secant tangent, and the integral of secant squared is the tangent of x dx. Or sorry, the integral of secant squared of x dx is tangent of x. And then I'd go through and I would use the recursive method on this. So I just want to remind you that that's out there because you may need to use this in your homework set. As usual, if you have questions, let me know. Send me a screenshot. You're welcome to text me and we can set up some online office hours as well. You have your Pearson Connect to a Tutor for help. And of course, if you have questions, I'm happy to answer them anytime. These are long problems. Don't give up on them. It's really important to show all of your work because if you start skipping any steps, that's where you're going to start making mistakes. Good luck, and I hope you enjoy these. They're kind of fun problems because, of course, we get to use some trig.